We've gone over the three major pathways by which nitrogen is lost from ecosystems in gaseous form. And this is a good place to go into the atmospheric roles of these nitrogen-containing gases. To a certain degree, we're going to be backtracking and thinking about atmospheric processes, but it matches up well with understanding nitrogen cycling. The four nitrogen gases that we talked about have different roles and consequences for the atmosphere. So we're going to think about ammonium, and then we've got NO, N2O, and NO2, which we haven't talked about much. Ammonia is a base, and it reacts with acids. So when it enters into the atmosphere, it has a neutralizing effect. So for example, if there's sulfuric acid that's been put into the atmosphere by a volcano, ammonia can react with the sulfuric acid to form ammonium sulfate. This then can enter into solution and rain down on ecosystems. In addition, ammonia that's volatilized from soils can enter the atmosphere, but sometimes, depending on the conditions, can be taken up directly by plants through their stomata. And there's examples where if it's relatively wet and ammonia gets trapped in the water, it enters through the stomates and back into the plant. So it's actually not unheard of ammonia being taken up by plants through stomates. It's hard to quantify this in many ecosystems, but it's definitely a pathway for ammonia. Now, NO and NO2 are often talked about as NOx. So we've got nitric oxide and nitrogen dioxide, and we generally refer to these as just NOx. The interconversion between these two are relatively quickly once it enters into the atmosphere. NOx is very reactive. When it enters the atmosphere, it often reacts with carbon monoxide, methane, or volatile organic compounds to produce ozone. It serves as a catalyst for this interconversion of oxygen to ozone. It's a little bit complex to get into the details right here, but when we have situations where there's a lot of methane or carbon monoxide or VOCs in the atmosphere, and then you get a lot of nitric oxide being produced, for example, then you can form a lot of ozone. And a lot of the air quality issues that we have in cities are places where there's a lot of carbon monoxide, along with a lot of nitric oxide that enters the atmosphere. And then that generates a lot of ozone. Methane, VOCs also are associated with ozone production. So once NOx gets into the atmosphere, it's really an important component for generating smog in the troposphere. And smog in urban areas. So having a lot of NO, and some kind of carbon-containing compound generates a lot of smog. In addition, NOx can also get turned into nitric acid. And this is important because when nitric acid comes down, it's a form of nitrogen, but also it's a form of acidity. And we can have acidification of ecosystems associated with acid rain. And it's the nitric acid, for example, that's a large component of acid rain that ultimately was produced from NOx in the atmosphere. N2O is a lot more stable and a lot less reactive than NO or NO2. The mean residence time of N2O in the atmosphere is on the order of 150 years. It's important because it has somewhere on the order of 200 times the ability to capture infrared radiation. So it's just 200 times more efficient per molecule in absorbing infrared. That means its global warming potential is just a lot higher than CO2. Small amounts of N2O being released from an ecosystem can more than outweigh any CO2 that an ecosystem is taking up in terms of global warming potential.